I'm going to move on to our next calculation here, which is the O2 content equation. The O2 content equation can be calculated for either arterial or venous blood. So doing arterial first, the C small AO2 arterial content is calculated by multiplying hemoglobin times 1.34 times arterial saturation, S small AO2, and then adding the P small AO2, which is arterial PO2, times 0.003. This equation is found on page 9.7 or 9-7 rather in your Oakes book. It looks a little bit different in that he's using 1.36 and 1.39. I'm not sure why, but 1.34 is more typical, so that's what we'll be using. And then I've got some normal values to plug into this equation to carry it out. So plugging in the values that I've been given, a hemoglobin of 15, which is actually a pretty normal hemoglobin level, and then times 1.34 times 0.98 for the SAT, which is a pretty normal SAT, and then adding the PO2 of 95, pretty normal for that too, times 0.003. So I'll begin to carry out the calculation now. So multiplying 15 by 1.34 by 0.98 gives you 19.7, and then multiplying 95 by 0.003 gives you 0.285. Adding those together gives a value of 19.98 volumes percent. And the units for this are expressed usually in either grams per deciliter or volumes percent, because grams are a volume and the percentage, or I should say the grams per deciliter, turn out to be a volume that is the number of grams over 100, and so it's expressed as a percent. So you can use either one of those. The hemoglobin comes in grams per deciliter, but the ADO2 or the O2 content equation is expressed either way. And if you look up the normal value for the arterial the arterial content, then you should find that it's about 20 volumes percent, which is approximately what we've calculated. So now we're going to calculate with a different set of values that are not quite as normal. So I have them here, and I will plug them into this equation. So doing that, I get 13 times 1.34 times 0.94, and then add 82 times 0.003. So carrying out that calculation, I get 16.37 plus 0.246, and then adding those together, I get 16.62 volumes percent. You may have a question, by the way, about how many decimal places to carry out the problems. As a rule, you don't want to carry out more decimal places than you have in your original values. We don't have any decimals. Oh, sorry, we do have a decimal right here, 0.94. We also have one here, though, 1.34. And then we have one here that goes out to 3 places. So I usually do this one in 3 places, this one in 2 places, and then my final answer in 2 places. But, you know, you'll just, since you're doing multiple choice problems for now, you'll just do the calculation and see which one that you have that's closest. So now we want to calculate the venous content. So it's the same formula really, but just with venous values in it. So instead of the arterial saturation, we use the venous saturation, and for the PaO2, the arterial PO2, we use the venous O2, and then that'll give us the venous content, or the content of oxygen in the venous blood. And so I've plugged in here some fairly normal values, and I'm going to use those to do the calculation. So writing out the equation first and then plugging all these values into it. So I've got these values plugged in, 15 times 1.34 times 0.75, and then add 40 times 0.003. And by the way, these are the normal values for these. You can see the hemoglobin in your oaks on 5-3, and then all of these values for oxygenation on page 2-1. So these are the normal values for venous here, and I used the normal values for arterial in the previous equation. So carrying it out, I get 15.08 plus 0.12, and then adding those together, I get 15.2 volumes percent. So I'm going to use some values that aren't quite as textbook and carry this equation out again. So plugging in those values, I have 13 times 1.34 times 0.71, and then I add that to 34 times 0.003, and I get 12.37 plus 0.102, and then adding those together, I get 12.47 volumes percent. So that's how you do the arterial and the venous content equations.